So today we're going to get into hypothesis testing. Yay, okay. So you may have heard of this a little bit, and if you've had a stats course, or maybe you did a little bit in quant, I'm not sure. I know in quant you do the standard deviation and average and means and those kinds of things, but here we're going to test for outliers. Did y'all do that in quant? Test for outliers? Okay. We'll do a little bit of that today, and then we'll look at the t-test and the f-test. And we'll focus really not just on the statistical tests, because they're pretty easy to do, but to be able to explain them and understand how to explain them and how to defend your work if you use them. Okay, so this is the scenario. We're training a newbie at DW Labs. Okay, we have a forensic chemist who we want to recertify on the equipment, so we go to the vault and pull out a recent seizure. Yes. Oh, thank you. How about that? Okay, there we go. We're training this newbie. Okay, and we have two people. We have a forensic chemist and a new person, a new hire. We go to the vault and pull out a recent seizure that's been analyzed carefully to be 13.2 plus or minus 0.1 by mass cocaine. And so those are our samples. So we have the trainee and the forensic chemist analyze these samples 10 times. So we want to get their precision. We want to see how accurate they are. And so we can certainly calculate those things with the means and standard deviations. But this is the real question. Are they the same or different from each other? So we have two analysts, right? Do they get the same answer? And if they don't, then in what ways are they different? So that's a very valuable question, because if I'm in charge of a lab and I receive the incoming samples, I don't want to have to be worried about who I give the assignment to. That makes sense. You don't want to have more trust in this employee versus that one. You want them to be interchangeable because you've got a workload, and you don't want to have to worry about that. So that'd be in an ideal world or perfect world, there'd be no statistically significant difference in accuracy, which would be the means, or the precision or the variances between the lab personnel. There's always going to be some difference, but is it statistically significant? That's the question. If it's not statistically significant, then it doesn't bother me to assign it to you or to assign it to you. It doesn't, I don't want to have to be in a situation to say, oh, this is a really important case, I better give it to this employee. I want everybody to be reliable and to give me a statistically defensible answer. And likewise for at the state level, they don't want the different labs to be statistically different. They want to be able to say, well, this lab is just as good as that lab. And so that's why they have those standards and the quality assurance. Okay, so here's the results. So let's first just look at the results and see if they look good. Our true value or accepted value is 13.2. And they all look pretty good to me. They're all in the 12.9s. There's a 12, that's kind of low. There's a 15. Okay, do you see the 15? Yeah. That's in the trainee column. So what do you have to say about the trainee compared to the forensic chemist? Not as precise, right? You see there's much more scatter. Just looking at the numbers, you can see there's more scatter in the trainee. It's a little hard to see things in a table, though, right? It's nice to just rank them in order. So here's a plot from Minitab. This is called an individual plot. And so you can go in Minitab. You can download a free trial for Minitab, or you can download it on the campus computer if you're on campus, and start playing around with the options in Minitab. And this would be under graphical methods and individual plot. And now you can really see the trainee on the left and the forensic chemist on the right, and see the scatter. And so that true value I've drawn with the green bar and a plus or minus 1 standard deviation, so that should get 65% of the variability at least of the true value. And you see the forensic chemist is pretty much all of their data is between those bars, whereas the trainees on this scale pretty much all over the place. There's a lot of variability. What do you have to say about that data point number 15? It could be an outlier, exactly. It could be. And so we'll look at that. If you were to look at the means, that's what the little blue cross point is. So the blue line connects the means of the two data points. So it looks like the forensic chemist mean is within the error bars of the true value. What about the trainee? That mean is low. Okay. So even with that outlier, the mean is low. Okay. Taking that outlier out will make the mean even worse. Okay. So that'll push your answer even further away from the true value. And that's emotionally puts pressure against you throwing out that outlier, right? But you can't go on emotion. If that really is an outlier, then you pull it out, even if it makes your answer worse. Okay, because what you want to know is how did the person truly perform, not did they get the right answer? Because you may not know the right answer. In a questioned item, you wouldn't know the right answer. So you need to know how the trainee performs. Okay, but when you know the right answer, there's a lot of cognitive dissonance about pulling yourself further away from the right answer by throwing out an outlier. So you can't let your emotions get involved. So are they accurate or precise? I mean, we could make judgments on that. It's just difficult to. Well, let's ask this question: what are the benefits of the graphical methods? We saw it on the table and we saw it in the graph. So in your own words, what do you see? Yeah, it's. Mm-hmm. Yeah, in terms of communication too, because you're communicating to others when you present your data. Does this communicate better? It's easier for the audience to understand. It would be easier for a jury to understand. It'd be easier for people who read your reports to understand if you could use graphical methods. Okay. Here's a box plot. So notice how the individual points are missing. And this takes the average and then the 25th and 75th percentiles. So that range contains 50% of the data. So in here is 50%. Okay, so this it's called a box and whiskers plot. These are the whiskers here that stick out. So that gives you the minimum and the maximum, and that's the range. And now Minitab does its statistical test to determine if it's an outlier automatically in a box plot. And so it's telling us that 15 is an outlier. It also shows you the median, which is the middle data point. And this is the mean, which is the average. And notice they're slightly different. The median relative to the mean will tell you how the data is skewed. And so this is saying that this data is skewed to low values because the median falls below the mean. Let's see, maybe that's the opposite. No, that's the opposite trend. The skewed data points will pull the mean away from the median. Okay. So the median is what we typically say the most probable data point. Okay, and so then here we have the mean, median, and the range for our forensic chemist. There's no whisker that comes out the bottom because we saw from the individual plot, all of those data points are right there. And they happen to be right at that quartile barrier. Now, we said that the graphical methods communicate well, especially to someone who's new to the data. So they see this data, they can look at it and kind of understand the characteristics of the data. But there are some problems with graphical methods. So what's the problem with the graphical method that you see? What are you missing? When you look at the graphical methods, there may be questions that you ask that you can't really get answers to from the graphs. Yes, it's missing, like in this particular example, you're missing the data point. So I really don't know how many data points I have. I could have 3 and still get this plot, and I have 10. You can't really tell the difference between 3 or 10 in one of these plots. So we're missing the data points, but you also said another one, missing numbers. Let's focus on the numbers. What kind of numbers are missing from this? It's a graphical thing. We see a y-axis that tells us our value, which is % cocaine in the sample. But we're missing a lot of numbers in this chart. What are some of the numbers we're missing?
I guess the number of trials.
Number of trials. There's a bunch of numbers missing.
Standard deviation.
Yeah, we don't actually have a number for the standard deviation. We see this range, but we don't see the number. We don't have any number we can write down. What are some other numbers we're missing? The actual mean, the actual median. These are so graphical methods. They summarize things, but you're missing the numbers. So we really can't compare numerically the standard deviation of the trainee to the standard deviation of the forensic chemist. So we can see them visually, but we can't see them numerically. And so there's times for each. Notice how the standard deviation takes that whole set of data and reduces the precision to one number. And then the median or mean, when you take those and compare it to the true value, you can get an absolute error or a relative error. You know, percent error, that would be a single number that would tie to accuracy. So we want to know about percent error. We want to know about standard deviation, maybe the range, that's a number. We could probably calculate it here. The top number is 15. The bottom one is like 11.5. So we could visually see what the range might be. And so let's go through Excel. And actually, I would like for you guys to take this data set. I'll put it up on Blackboard, the B and C columns of the data, and want you to go through and basically create a spreadsheet that has every one of these formulas in it. And then you can upload that Excel sheet for one of the homeworks. So the mean or average, obviously this is, there's a formula in Excel called average. So if you type in that and give it the range, then it'll calculate the average. So this is pretty easy. We've got the average for the trainee and the forensic chemist, 12.9 for the trainee and 13.3 for the forensic chemist. So you see the forensic chemist is very close to the true value. The trainee is about, 0.3 low. Then the range, look how tight the forensic chemist is, 0.6%, and the trainee 3.5%. And then the standard deviation. So here in Excel, we have this little appended .s. Since we have less than 15 data points, we'll use the sample standard deviation. So STDEV .p would be the population one. And then you put the range in there.
Are you using .p?
We're using .s. Since there's only 10 data points. Yeah. And again, that's the more conservative standard deviation. It's dividing by the degrees of freedom instead of the total number of data points. Now, if we look at this standard deviation, we could say that, they're both, let's see, even within plus or minus one standard deviation, we're going to capture the true value. So we're at the forensic chemist is 13.3. If we just say plus or minus one standard deviation, they're less than one standard deviation away from the true value. So that's great. The trainee, 12.9, plus or minus 0.9. Okay, so 12.9 plus 0.9 gets us to 13.8. So again, we're within one standard deviation of the true value. So, that's a way that you could say, well, they're accurate. It's within their error bars, but their precision isn't what we'd like compared to the forensic chemist. But they are getting the true value within their error bars. It'd be nice to tighten up their analysis, though. So the range contains 13.2. So we would say that the trainee sort of captured the true value with their analysis. There is a bias, though. And then the same with the forensic chemist, their range also captures the true value. We really couldn't tell that necessarily from the graphical methods, but it's nice to have the numbers. Okay, so like, numerically they both seem to be accurate because their means and standard deviations contain the accepted value. So let's look at these different error types. So this is where we get into hypothesis testing. And when we do hypothesis testing, we have a null hypothesis. Null is another way for zero, word for zero. So it's our zero assumption. We're saying that it's H0, this null hypothesis. And what's interesting is we can't know the truth. We can only know what our statistical tests tell us. So it's sad that we can't know whether our null hypothesis is true or false. We can do a statistical test, and we have criteria for whether we reject the null hypothesis or fail to reject it. So we're sort of trying to reject it. So the null hypothesis for that data point number 15, or that value of 15 in the trainee, would be the data point is not an outlier. So that would be the null hypothesis, that the data point is not an outlier. Okay, there's other tests that we're going to do. The t-test. The trainee and forensic chemist data sets are from the same population. Now, what does that mean? Well, there's several ways to interpret this null hypothesis. This could mean that the samples that the trainee sampled were from the same group of samples that the forensic chemist sampled. Do you see how if you have a seizure of identical little plastic bags and they both analyze 10 of them, and this is the null hypothesis is that all 10 of those bags for each of them came from the same group. And if they came from the same group, they should have the same mean value. I just want to make sure I get everybody's eyes on that one, okay? So if they have equal means, we have to assume they came from the same group. Even if the trainees' baggies were blue and the forensic chemist baggies were clear, we analyze it, we say, well, the means are the same, so they're probably from the same batch, even though they have different plastic bags. Okay. In reality, if you saw things come in with different colored plastic bags, you would just naturally separate them, okay, and analyze them separately. But that's what this test is. The null hypothesis is that they're from the same population. Now, they could be from the same physical population, but because they go through two different analysts, that can be a population as well. So that means that there could be a forensic chemist's answer and a trainee's answer. And so even though the physical bags came from the same group, they went through two different analysts, and that could shift the means apart. And so that's a way to separate populations too. That's what we really don't want. We don't want our two analysts to present data to where we think that came from two totally different batches when they really came from the same batch. So that would be sort of an artificial separation of these samples. So we want to test the trainee and the forensic chemist to see if their means are the same. Because if their means are the same, that means there's no accuracy difference between the two. We know physically they came from the same samples in the lab, but they went through two different analysts. And so this is not just testing the samples in the lab, it's also testing our analysts. And that would be the t-test. And this is the null hypothesis for that t-test, that the data that came through the trainee and the data that came through the forensic chemist have the same means, which means they're from the same population. Okay. And then we'll do an F-test for equal variances. And this is saying that the precision of the trainee and the precision of the forensic chemist are the same. So those are our baseline assumptions in all of these tests that we're going to do today. And notice how the best situation, I guess, would be what your null hypothesis is, that there's no difference in population, that there's no difference in variance, that there's no outliers. If if that is the true situation and you fail to reject the null hypothesis, then you got the correct answer. If it's not the true situation, meaning there really is a difference between the two analysts, and you reject the null hypothesis, you got the right answer. And then these are the type 1 and type 2 errors. If you reject it incorrectly, then that's a type 1 error. If you fail to reject it or you accept it incorrectly, then that's a type 2 error. The different types of tests may have what we call a positive or a negative result. And so if this is a positive result, like you're doing a COVID test and it should be positive, okay, and you reject it, okay, then that would be a false negative. It should have been positive, but you rejected it, and it's a negative. If it's supposed to be negative and you accept it, that would be, again, a false positive. So we have those different terms that we use, and they can be totally different percentages. So sometimes we want to twist the test so that we don't have false positives, but we can handle a false negative. Other times we're so worried about a false negative that we tighten it up on the false negative and we can handle a false positive. Okay, so this type 1 error, type 2 error analysis is a more advanced topic than we're going to get into. I just wanted to introduce it here, that these two errors are where we get our terminology of false positive and false negative. Okay. So this is the statistical way to make this decision. So we have our null hypothesis, and if the probability that the null hypothesis is true is less than 0.05, then we reject that null hypothesis. So in words, we're saying if the probability is less than 5% that the null hypothesis is true, then reject it. It's a pretty stiff bar, isn't it? If there's only a 6% chance, or even it says less than 5, so if there's just a 5% chance that the null hypothesis is true, then we're going to keep it. So that data point, we think it's an outlier. If there's just a 5% chance that it really is in that population, we're going to keep it. So we need at least a 4% or less, or less than 5%, 4.9, whatever, then we're going to throw it out. But it has to be 4.9 or less before we can throw it out. So we don't want to throw data out. We want to include it. Maybe that is a real analysis data point. Okay. Same thing with the means. I mean, are we really going to call our technicians different? If there's just a 5% chance that those means are the same, we're going to say they're the same. If there's a 5% chance that their precision is the same, we're going to say it's the same. Okay. And so that 5% or 0.05 is called alpha. And 1 minus alpha is your confidence. So an alpha of 0.05 goes with a 95% confidence. So we hear that all the time, 95% confidence. And that means your alpha is 0.05. So that's that bar for the probability. It has to be less than 0.05 before you can reject it. And the other thing too is if you can't state your null hypothesis in any given statistical test, then you shouldn't be using it. Okay, so this is a real critical thing. If I'm ever in one of your capstones or anything like that in the future, I'm going to be asking you about alpha and asking about your null hypothesis. And if you ever report a p-value on anything, I'm going to ask you about, that's the probability. P stands for probability, but what is it a probability of? And that's when you state your null hypothesis. It's the probability that this data point's not an outlier, or it's the probability that my means are the same, or it's the probability that my variances are the same. So if you can't state your null hypothesis, you don't know how to use the p-value. We get p-values most frequently in this course with our linear regressions, so our ANOVA output. And so we have a b, an intercept, and a slope, and a p-value. So what's our null hypothesis for those? What's that? So we have our ANOVA, we do our linear regression for our data, and we have our intercept, and you have the intercept, the value, the uncertainty, and then you have a p-value on that same row. So that's the p-value for B, for the intercept. That's the probability of something. So what's our null hypothesis for that B? That the intercept is 0, that it's not significantly different than 0. Yeah. So you say that random noise gave us that number, and you can calculate the probability of that because it can analyze the noise in the data, and its default is that B is 0. The intercept goes through 0, and if it's really different than 0, that p-value will be low. It'll be much lower than 0.05. In PChem, sometimes your intercept or your p-values were 10 to the minus 17, way lower than 0.05. You know, for the iodine lab or for the carbon monoxide lab and all of those p-values were really low because your intercept was significantly different than zero. And your slope, same thing, was significantly different than zero. A zero slope would be a straight line across. And your data just scattered all across that. There's no slope to the data. It's on zero. Basically, it's saying all you have is noise. You have everything surrounding zero, and it's just random noise. There's no slope, there's no intercept, and your p-values would be really high for both of those. But if it has a trend, it has a strong slope, and it's off the axis above or below, and that intercept is not zero, then you would have really low p-values. So just remember that when you do a linear regression, that your null hypothesis is that the M and B are zero. And that if they're different than zero, it's because of random noise in the data. So that's your null hypothesis for those two. So let's do a top hat. So what is alpha for a test of the null hypothesis at 99% confidence? It's a numerical result. So just type in alpha if you want to do 99% confidence. I'll extend it one time, 15 more seconds. Okay. Two more people. Three, two, one, and time's up. Okay, good job. 21 of you got 0.01. And I think the one is probably, it's like 99% confidence, 1 minus that, you know, or 100 minus that would be 1. So make that a decimal equivalent from 1% down to 0.01. You got it. So great job. Okay, so then we'll go to actually using some of the tests. So let's look at that outlier. So this is Dixon's Q-test. I've only seen this used in chemistry. It was put in the Analytical Chemistry Journal back in '91. This is a table from Skoog, West, and Holler that I had when I was an undergrad using these Q values. We'll learn how to use the Q-test because, again, it still shows up in analytical chemistry, but we'll learn in the next set of slides or the next panel that the Grubbs Z transformation is probably more useful now or more used now, more common. But still, they're both used, so I'll teach you both. So here's the thing. If you know you spilled your sample or you saw something wrong with the sample or whatever, you can make a note in your notebook and you throw that out. That we only use outlier tests when we don't know what's wrong with the sample. So if you know that something got spilled or if something was weird with the pipette or whatever, throw that sample out and redo it if there's time. If there's not, if it's an involved process or whatever, then you've just got a bad run. And you make a note and you throw that one out. Don't put garbage in because you'll get garbage out. Okay. So this is when you have no other reason to suspect that there was a problem with that data point and the result is just off from the others. So what we have to do is we have to determine this gap and range. So it's a ratio. This Q experimental is a gap and a range. The gap is the questioned data point. You see, that's what the question mark is. The questioned data point minus its nearest neighbor. And that could be above it or below it. And so it could be a positive or negative number. So we're going to take the absolute value. Okay, so we just want the gap. We don't care about the plus or minus. We just get the gap. And then we divide by the range, the max minus the min. And that's our Q experimental value. And then here's our null hypothesis, that that question data point is not an outlier. And then we have our alpha values. Okay. And we have our number of values that we have, our number of data points. And so here we are at alpha 0.05. We've taken 10 data points, so we have the 0.466. That's our critical value. And then here's our hypothesis test right here. So if Q experimental is greater than Q critical, then we reject the null hypothesis. So if Q experimental is greater than Q critical, we reject the null hypothesis. We say H0 fails. It's not true. Okay, so we can do this in Excel. We'll look at it in a second. Okay. So let's look at the Z transform. Well, let me go ahead and jump ahead and find it. Okay, here we are at the nearest neighbor. Okay, so here we have the maximum value. Here, this 15. Looking at all of the data, we have a 13.0, a 13.2. Here's a 13.3. So that's the nearest neighbor. And so we calculate that gap. Okay, so 15, 14, so 1.7. Okay, and then we divide it by the range. So 15 minus 12, is that the small? No, 11.5. So it'd be 3.5. So 1.7 divided by 3.5 would give us this Dixon's Q-test, this 4.86. That's that range. Oh, that's the gap over the range. And then here's our critical value. So this is Q, this is Q critical that we got from that table at 95% confidence and 10 data points. So our test, because 4.86 is greater than 4.66, then we would say it's an outlier. Okay. Now we also have a maximum data point here on the forensic chemist. This was 13.7. It was the largest data point, and its nearest neighbor is 13.5. So we calculate that gap over the range, and it's 0.33. Here's the Q critical, and so 0.33 is less than 0.466, so it's not an outlier. Okay, according to the Q test. Now let's go back a slide and go look at the Z transform. This one has got a little bit stronger pedigree. It's supported by the ISO, the International Standards Organization, and the ASTM. And it's based on a normal distribution. So we have these Z critical values, which look familiar, right? At alpha 0.5, this 1.96 is that Z value to capture, that's how many sigmas would capture 95% of the area under a normal distribution curve. So it's nice in that it uses that same Z table that you're familiar with. It's based on population statistics, so there's not a number of data points to use. And that may be a weakness if you have less than 15 data points. It might give you an outlier when you really don't have one. Okay, so that might put in favor with 10 data points, put the Q transformer, the Dixon's Q test up a little higher than this. But so here it is. It's also used if there's no known reasons for producing an outlier data point. It's based on a Gaussian distribution that has a mean of 0 and a standard deviation of 1. So here's our mean of 0 and our standard deviation of this curve here of 1. And so this x-axis is Z. and we're calculating the z value for our data point. Okay. And so you can compare your z value to the various cutoff values in this table to decide if it should be excluded. So the null hypothesis, again, is the question data point is not an outlier. And so then if a z question mark is greater than z critical, then reject H0. What do we need to do to calculate z? Well, look at this. Instead of taking the question data point difference from its nearest neighbor, we see how far it is from the mean. Does that make sense? We're seeing how far is this question data point from the mean value. And then we divide by the standard deviation. So when we divide by, let's say our standard deviation is 5. When we divide by 5, essentially we're shrinking our distribution to match this right here. If we take our standard deviation and divide by 5, since we're dividing by 5, we're shrinking this curve down to where now it's in units of standard deviation, and so in our data this would be 5, but we divided by that, so we kind of normalized it to this curve. And then we're calculating how far away from the mean our data point is. If our data point is way out here, look how low the probability is of having a data point here if this is the standard deviation of the curve. Notice how it drops down. And if our data point is here, but Z95 is here, 1.96, we have less than a 5% chance of getting a data point that far away from the mean. So we would say it's an outlier. You see what it's testing? It's saying, how far away from the mean am I? And here's my standard deviation. Here's 1.96. If I'm beyond that, there's less than a 5% chance that that data point is from this distribution. Something else happened to push it there. And so that's what we would say as an outlier. What we're trying to test is normal variability will spread our data out. And we're trying to see, was it a special cause? Was something wrong with that data point that we didn't pick up? You know, we pulled a pipette sample up, but there was an air bubble in there, and so we delivered slightly less volume. That's not random. That's actually a systematic error. That's going to throw that data point way off. So here we test that with the Z-transform. We calculate that distance from the mean, 2.5, and we calculate that actually the Z value, this distance from the mean divided by the standard deviation, we get 2.5. And then here's our 1.96, which is our 95% Z value. And so the Grubbs test tells us this is an outlier. So what do we do with this? Why do we get two different answers? I've got a problem now. It's frustrating, isn't it? You get two. Is it an outlier or not? Which one of these took into account the number of data points we had? The Q test. The Z transforms based on a population, and we don't have a population. We've got 10 data points. And so even though the Z transform, the Grubbs test, is telling us this is an outlier, it thinks we really know what that standard deviation is. And we may not know it, right? Because we only have 10 samples, and if we took 15, if we took 5 more, then these answers may converge, and it may not be an outlier, you know. But it's thinking we really know that standard deviation, and that we really know that mean. And so again, if you don't have a population, if you don't have 15 or more samples, then the Grubbs test may be less reliable than the Dixon's Q test. So that's an example too when you want to use the Dixon's Q test, because if you have 5 samples, 5 measurements, you definitely want to use the Q-test because it'll take into consideration that small sample size. Okay.
So would you just trust the Q-test if it's sample size less than 15?
Yeah. Yeah. And so we'll go with the Q-test on this one and say that it's not an outlier, and we'll put in there because n equals 10, which is less than 15. Yeah. Yeah. So we're good. Okay. So we calculated our accuracy and precision without the outlier. Notice that the bias or the error is our mean minus our true value. Notice the order here. And this is similar to your control charting. I really insist on like today's measurement, you subtract yesterday's measurement from today's measurement. Because if yesterday's measurement was smaller and then today's is bigger, it's going to be a positive number, which means it went up. Okay, if you reverse that, today's value is bigger, but you'd have a negative number for today. So the daily change would be wrong if you don't subtract it the correct way. Same thing with this error. If your mean is above the true value, I want to see a positive number, which says you were high. So the positive and negative tells you whether you're high or low. And so the order matters. And so you just think about it. You know, if your mean is above the true value, you want that to be a positive value. And there's only one way to get that. That's mean minus the true value. You had a question?
Yeah. If the sample size is exactly 15, which test do we use? The Q-test or the
I would use the population one, the Z transform, yeah. And the same thing with the standard deviation. I would use this standard deviation .p for population. If you calculate it by hand, it would be over n, not the over n minus 1. Okay, so then percent, so you can take that difference, again, mean minus the true value divided by the true value. So you're saying what percentage of the true value is in question times 100%. So that's where we get the percent error. It also has a sign as well. So our trainee is absolutely, it's a 0.33 low, which is 2.5% low. Now we have 2%. We have 13, the true value is 13.2% by mass cocaine. And now we're talking about percent of that value. So we're kind of like a percent of a percent, okay? So that's when your data is in percent, it can get really confusing because you're calculating the percent of a percent, okay? So if you like get a brain freeze on that, just back up and think of what you're calculating. So, okay, so when I said, is this accurate? I would say this is, fair accuracy. Below or greater than 5% error would be poor. If you're within 5% of the true value, that's pretty good. Okay. If you're within 2%, that's good. And if you're within 1%, that's excellent. So these are my categories. This is what I've used for years. DW says. Okay. But that's just been my experience. When people talk about their accuracy, and they say, well, we have good accuracy under 2% error. That's sort of the language that I've heard. So I'm just kind of giving you my take on things. If you're more than 5% off, that's a problem. Yeah. You need to find the source of your bias. Recalibrate your pipettes or something like that. Who knows? Okay, so then we come down here, standard deviation. We did the population standard deviation, even though it's not a population. Let's see. Yeah, okay, so I'm just showing you the difference between the sample standard deviation right here. So this is the sample standard deviation. And here's the population standard deviation. And you can see how the sample standard deviation is larger. That's the more conservative estimate. And if you're trying to write down all the numbers and fill in the blanks, you can do it on the video. So like if I move on and you're not quite done, don't stress. You can definitely go back and get it on the video. We have our confidence levels and so on, and we can say, are they precise? So here we are. this x plus or minus 1.96s is going to be here 12.2 to 13.5. It definitely contains our true value.
So the percent error 2.5 is negative 2.5.
Yes, here, because we're low, we came in at 12.8 or 12.9, and we're below the true value. So that 12.9 minus 13.2 gives us a negative value. So it's showing that we're low.
But you would still consider it a positive when you're looking at the...
Oh, yeah. So up here, I'm sort of saying how far away from it is, whether positive or negative. Yeah. Yeah, that's a good question. So. And then here, our relative standard deviation, we take the standard deviation and divide it by our mean value, 0.07. Let's see. Yeah, and then we take that times 100%, so it becomes 7.2. So that's our coefficient of variation, the CV value. And it's also sort of a percent that we can use this table for. And so our CV is 7.2, so that's poor precision. So even with our little gauge, we're greater than 5% error, or 5% uncertainty. And so it could be better. So right there, just with our subjective criteria, we know the trainee has to improve the precision a little bit. Now let's look, if we throw that outlier out, our precision should improve. Okay. And so if we throw that 15 out, then like I said, our mean is going to drop further because we got rid of that data point that was pulling our mean up. And our percent error is now, for absolute error, 4.3% negative. So we're low quite a bit. We're pushing that poor region, the boundary of 5%. We're not quite there yet. So still have we have fair accuracy. Our standard deviation has decreased because we got rid of that large data point, that 15. Our CV improved to 4.6. So without that outlier, we're saying we have fair precision. Let's compare this to the forensic chemist. We kept that data point, and so our percent error is 0.5%. So that's excellent. And our precision is good. So our CV is 1.5%, and that's in the 1 to 2 range. So that's good precision. And then again, this is just a reminder on those two equations. I didn't really emphasize that as I should in the propagation of uncertainty set of notes, but here's the relative standard deviation, and here's the CV. It's that RSD times 100%. Okay. Now to report a standard deviation for the whole lab that includes both of the trainee and the forensic chemist, we pooled the standard deviation. We calculated this during our measurement exercise that one day. So this is how it's calculated. We need the pooled standard deviation for the t-test for equal means. And so what are the numbers that would go in here? Let's just call the trainee N1. So since we got rid of that data point, this would be 9 minus 1. This would be 10 minus 1. Let's go back and get those numbers. So the S1 is 0.58. And 0.58 and 0.2. So we could calculate those. We threw out the outlier. Yeah, so without the outlier, we recalculated the standard deviation. And that would be more accurate. If it really is an outlier, then this would be a more accurate standard deviation for our trainee. And the pooled standard deviation, again, is needed for that t-test for equal means. And you can see this. We have the difference in the means divided by the pooled standard deviation. times this ratio of all of our data points. And so this right here would be 9, 10, 9, and 10. So we can calculate this experimental t-value, and we'll have the same kind of thing. If t experimental is greater than t critical, then reject H naught, the null hypothesis. So let's look at this. Since our trainee could be high or low, we have a two-tailed t-test. So there's a one-tailed where you can only have, values that go in one direction, or the two-tailed. We're taking the absolute value of that difference, so we get a positive number. But because it's a two-tailed, we're trying to see how far it is, either one side or the other. And so we have to use half of our alpha. So 0.05 alpha for a two-tailed test, 2.5% could be on this end, 2.5% could be on that end. Okay, so we divide alpha by 2. And so our critical values are going to be this t inverse 0.025 for the alpha. Okay. All right. And then here's our and so this 8, this is our 9 minus 1. And so you can look this up in the table, but Excel does this. You can calculate the t inverse values using Excel. So you have this in Excel. This we have all of these values. The pooled standard deviation is calculated here. Actually, it looks like I calculated it with both outliers pulled out, so that's not cool. But redo that. This should be 10. This should be 10. Okay. And so then we have the 2.69 and 2.75. Those are the t-table values. And so here's our t-test for the trainee. This, and this t-table, this is the t-table value. So 2.8 is greater than 2.6. So that's, again, if we just take the trainee data, that's what I did. Yeah, but just the trainee data was not using any outlier, not taking the outlier out. So without taking out the outlier, it says the means are not the same. So it means our trainee and our forensic chemist are giving us two different average values. If we take that outlier away, it actually gets worse because our mean drops down even further. And our experimental t-value is 6.74. So this is t experimental. And these are t critical values here. So 6.74 compared to 2.75, again, it's greater. So therefore, the means are not the same. And so this is saying we have a completely different answer between the forensic chemist and the trainee. Okay. So now we'll do the F test for equal variances. So our null hypothesis is that they have the same standard deviation. We can look at it visually and know that they don't. Okay. So we calculate F experimental. This is the easiest experimental value to calculate. It's just the ratio of the variances. So we go get the standard deviation for the forensic chemist and the standard deviation for the trainee, take the ratio. Now our trainee can be high or low, so we have a two-tailed F test. So the low value will be 0.025, the high value will be 0.975. See how that's 2.5 from 100? Okay. And so we could test it if it's above that value or test if it's below that value. So we have an upper critical F value and a lower critical F value. And notice we have both degrees of freedom in here. So this was the 9 minus 1 for the trainee, and this is the 10 minus 1 for the forensic chemist. So that's our upper value of 4.1. Our lower value would be the 0.23. And so here's our test. That experimental value, if it falls within the lower and upper F critical values, then do not reject H0. If it's greater than the upper or lower than the lower, then you reject the null hypothesis. So let's look at what the numbers give us. We'll come back and do that top hat. So here's our ratio of variances. So the trainee without the outlier divided by the forensic chemist is here, 8.35. The trainee with the outlier is 21.37. So these are our F experimental values. Our lower critical values are 0.25 and 0.23 for those. Our upper critical values are 4.03 or 4.10, 4.1. And we're at 21 with the outlier. We're at 8.3 without the outlier. So we're way beyond that, that critical value. And so since our F experimental is greater than the F upper values, then our variances are not the same. So we have a numerical test. We could look at the graphical methods and make that call, but now we have a numerical proof, if you will, that these two persons have different precision. So as a lab manager, I've got a problem. I've got to figure out how to get these two to come to the same answer with the same samples. And so we would just do some retraining, maybe walk along the trainee as they do their procedures and see if there's anything that stands out. You know, maybe it may not be their technique, maybe just their observation skills. Maybe the balance was dirty and they didn't clean it. Or maybe they're using a different balance, right? And they say, I'll use the balance by my workstation, and the forensic chemist has maybe a more precise balance or one that's in a better enclosure or a different place in the room. You know, if I'm watching them do the procedure and they do everything exactly the same pipetting technique and everything, I've got to look at everything. And I say, oh, I just noticed y'all use two different balances. Maybe that's the real problem. So there's, you know, in the future when you guys are managers, okay, you can't solve everything with Excel or Minitab. You've got to get out of your office and go to the lab and watch and see what's going on. In industry, that's called walking the line. So you go down to the production line and you walk the line and you say, okay, I'm looking at my numbers, but they're not really telling me everything. I need to physically see people do their jobs and see what I see. And that's your observation skills really are critical. So these are the null hypotheses used so far. Let me do this this top hat here. Okay. All right, this is a new type of question I'm excited about. Matching. I don't know how y'all do matching on your phones, but we'll see how it works. Can I come see? I'm gonna watch. Oh yeah, very good. Oh, that's good. You like this? It's a good question.
You just drive on the right side.
Oh, I see. You have to drive.
Oh, good, good. Uh-oh. Maybe it's not going so good. I got 1 out of 26. It's okay, too. Is that working? Yeah, good. And do you have to get to a point where you say, okay, submit the answers that you got? I keep extending the time. It's a little longer. Is it not behaving?
It's
Okay.
fine. It just
Okay. I'm nervous because this is a new tough question type for me too. So I think it's fun because something different than the just multiple choice or type a number in. Okay. Four more people. I'm going to let this one run out. So if you're on the fence, make your choice. Make your choice. All right, let's see how it works out here. What do the results look like? Okay, drum roll, please. Okay, so the t-test is testing for equal means. I changed that word to averages. Okay, q-test is an outlier test. z-test is an outlier test. f-test is equal variances, but that's the standard deviation squared. So if you can't have an equal variance without an equal standard deviation. Okay, so I changed that a little bit. So, all right, cool. Okay. All right. My mouse's battery's dead, so it's kind of hard for me to switch around. Okay. All right, so let's little bit of review. So these are the different conclusions that we come to. The null hypothesis used so far are that the training and forensic chemist data sets are from the same population. We know they're from the same actual samples, but they've gone through 2 different technicians. And so we rejected this null hypothesis, which means there's statistically significant differences between their final answers, their means. So their accuracy are different. And then the null hypothesis, the training and forensic chemist data sets have the same variance. We rejected that as well, which means there's a statistically significant difference in their precision. We can do some of this same stuff in Minitab, so I just have this on the video if you want to do that in Minitab, the two sample t-test, and here's how you set up the dialog boxes to get this plot. So this shows you the equal variances test. It gives the standard deviations and confidence intervals on the standard deviations, and so that kind of breaks your brain. It's not a confidence interval on the value trying to capture the true value. This is, here's my standard deviation and how sure I am of that standard deviation number. So, and then it gives us a p-value for the probability that the variances are equal, and it's less than 0.0005. Otherwise, it will round it up to 0.001. So we don't know what it is, but it's essentially reported as 0 to 3 decimal places. So there's no chance that those variances are the same, at least to this many decimal places. Now let's finish up with this lab samples. So there's a whole like 100-page guide on Blackboard called the GUM, the Guide to Uncertainty Management, and it's an ASTM guidance for how to take field samples and turn them into lab samples. Now this is a really complicated question. What if you have a drum of material that was seized, raw material, and you need to tell, you need to take evidence out of that and tell us what it is. Do you just take what's on the top? Do you take what's on the bottom? Is it homogeneous throughout? Is it liquid? Is it solid? Is it a mixture? This is a complicated issue, and that guide for uncertainty management will help you with some of those sampling plans. Some of these are really difficult, like this decide on the number of analyses. This ASTM E122 talks about what is an acceptable error. Okay, so if you want a 5% error, like 0.05, if you want that to be your acceptable error, and you know the expected uncertainty in the sample, okay, so what's the uncertainty in that drum of material? Who on earth knows? And so I think this ASTM is really difficult to implement because we don't really know what this sigma would be. And so in industry, I use this other sampling plan. It's sort of a rule of thumb. You may have heard people say, well, just sample 10% of the material randomly chosen, right? Well, in a drum of material, what is 10%? Right? It's a bulk material. So it's difficult to come up with the 10% rule. Plus, if you have packets of things, let's say you get, if you get 10 packets, 10% is just one packet. That doesn't seem right. So 10% may not be a good rule of thumb. And most of the time you have auto samplers, and so it's not a problem to do 20 or 30 samples. I mean, that's, you can make them up pretty quickly in these trays and set them on the instrument. So 20 is an easy number to do. And so let's say if we have 10 samples and it's easy to do 20, let's just do all 10, right? But if we get above that, let's say we get to 20, we could do all 20. If we get more than 20, maybe we should just do 10% of what's above 20. And so that's been the rule of thumb that was passed down to me. And that is, you test all of them up to 20 field samples in a lot. So you open up someone's trunk, you've got a couple of different boxes full of material. You open the boxes, you see they're all little individual packets, but maybe this group is a different color, maybe it's off-white, and this group is white. So you might say, okay, those are different lots. So you separate them into lots, make different colored bags, whatever. If there's something that distinguishes them, then you pull them off into different lots. And then you count each into that lot. So if we have, say, a huge seizure, 500 packages, okay, how many are we going to sample for 500? Well, we know we're going to do 20 of them, chosen at random. So what is 500 minus 20? 480. Then we'll do 10% of that rest of that. So we do 20 plus 10% of the remaining. So 10% of 480 is 48. So out of 500, we have 48 plus 20. We have 68 samples. So now we have a sampling plan. So out of 500 packets, we can pull out 68 at random. And we can be pretty confident that we've characterized all 500. Does this sound like a plan? Think about how long it would take to do all 500 and how redundant it would be, how unnecessary it would be. Once you've gone past 68 of them, you're just doing busy work and wasting resources and so on. So, but you've got to be sure that you've separated them into lots. What you're trying to say is this 500 are homogeneous, and then we can get by with only testing 68 out of that 500. So it's a little more conservative than the 10% rule of thumb. 50 would be 10%. And so this is 10% of the remaining over 20. So let's do a top hat on that, and then that'll end the day. And you can probably guess this will be a numerical answer. So how many lab samples should be analyzed of 100 small, apparently identical baggies of white powder? Okay, I'm going to let this one run out, so be sure to get your answer in. Come on, drum roll, please. 28. Yay, very good. So the first 20, you have 80 left over. 10% of that is 8. Add it in, so that's 28. Yeah, so good job, folks. Okay, very good. Y'all have a great day.